Alrighty, we're gonna go ahead and go. So on the bell work, it says Maria plans to rent a boat. The boat rental costs $60 per hour. She will also have to pay for a water safety course that costs $10. Maria wants to spend no more than $280 for the rental and the course. The boat rental is available only for a whole number of hours. What is the maximum number of hours for which Maria can rent the boat? Same thing with any type of word problem. You really want to filter through stuff. Okay, so the most important things that you can grab out are that the boat rental costs $60 an hour. She has a $10 flat fee for the course, and that's regardless if she even rents the boat. It's just $10 to go to the course, so that'll be kind of like our y-intercept. And she doesn't want to spend more than $280. And our answer needs to be in whole numbers, because the rental is only available for whole numbers of hours. What is the maximum number of hours Maria can rent the boat, and without exceeding $280? So this is actually a linear inequality. Okay, $60 an hour, that's going to be our like slope variable, plus 10. That's going to be kind of a y-intercept, if you could imagine it, if you were to put it in the form y equals mx plus b. But since we're talking about that we want it to be less than or equal to 280, that's what sets it up being a linear inequality. Now, if we are able to solve for h, we'll find out how many hours it would take for her to reach $280. So we'll proceed with solving with h. You get 60h is less than or equal to 270. Divide by 60 on both sides, and we get h must be less than or equal to 4.5 hours. Okay, here, that's the total amount. Like if they allowed you to rent it for half an hour, she'd be able to get 4.5 hours. But the question specifically states that it's only available for a whole number of hours. So the most hours that she can rent the boat without exceeding $280 is 4 hours, because it wants to be a whole number. If we go up to 5, her cost would be about $310, which kind of violates the time frame of her not wanting to be over 280. All righty, so that brings us to lecture. Get the slides up. Okay, so what we're going to be talking about today is graphing special functions. Okay, the types of functions that we're going to graph are the piecewise defined function, a piecewise linear function. Those are pretty simple. Most common ways that those are expressed to you, I'll give you an example. It'd be like f of x is equal to x plus 1 when x is less than or equal to 1, and then x when x is greater than 1. Okay, so a lot of them are pretty simple, but a piecewise function is it's taking multiple functions and it's isolating the domain. Okay, this is the key part. X less than or equal to, or x is greater than. Okay, for your signs, if you come across a less than or equal to or greater than or equal to, these correspond to a closed dot. Okay, and you'll see those. If you come across just greater than or less than, these correspond to an open dot. Okay, this is a key item, making sure you have a closed dot in the correct area and an open dot in the correct area. The piecewise functions really aren't that difficult. We just have to be very detailed about where our domain begins, where our domain ends. Okay, so we really want to be on point there. Okay, the next type of function that we're going to talk about is a step function. Okay, and step functions, they are discrete functions. They are not continuous. And they're called step functions because they kind of look like a staircase as you were looking at them. Okay, the most common step function is the absolute integer function. Okay, so here's an example of a step function. Okay, you want to make this note. For Desmos, to input a step function, you need to use the term floor with parentheses. Okay, and you would put whatever variables. You can put variables outside of it. Most commonly, it would be the floor of x. Okay, the way that the book is going to present them to you is with double brackets on each side. Okay, that corresponds to the greatest integer function. Once again, the cheat to put them into Desmos is you have to use floor of x. And I'll show you how to do that. Okay, the greatest integer function. Like I said, it kind of looks like a staircase. This is an example of it. What this means is that we're going to round down to the lowest integer, or to the greatest integer closest to it. So I'm going to write down a series of numbers. I'm going to take 1.1, 0.9, 2.4, 3.6, a negative 4.5, and a negative 3.5. Okay, and this all corresponds to the greatest integer function. Like I said, we want to round down to the closest integer with it. Okay, so integers are whole numbers. Okay, there's no decimals. And the key is we're going to round down. So 1.1 gets rounded down to 1. Okay, that's fine. 1.9 gets rounded down to 1. Okay, 2.4 gets rounded down to 2. 3.6 is rounded down to 3. Negative 4.5 gets rounded down to a negative 5. Okay, the key is we're rounding down. We're rounding down. So the negatives make it a little tricky because conventional wisdom would say, oh, I'm just going to round this to a negative 4. But understand negative 4 is greater than a negative 4.5. So we have to round down to a negative 5. Negative 3.5 gets rounded down to a negative 3. Okay, this is at the center of the greatest integer function, which once again is expressed to you like this. Okay, has two brackets, an x. Okay, that's corresponding to the greatest integer function. In order to, no. Oh, wait. Yep, you're right, Sydney. Sorry, good job. Thank you. Way to catch me on that. You are correct. It would get rounded down to a negative 4. Just want to round it down. And you can see, I'll bring up Desmos real quick. I'll show you how to input it. I'll show you what it looks like. Graphing calculator. Okay, like I said, to input any floor or the greatest integer function, type floor, parentheses, x. Okay, if there's a number outside of it, you just put the number outside of it and you can see that it expands it. Okay, if you want to shift it left or right, you have inside and outside that we'll talk about. But this is what it looks like. Okay, if I zoom in to where we can just see 1, you can see that anything underneath 1 or anything between 0 and 1 has been rounded down to a 0. Anything between 1 and 2 gets rounded down to a 1. Anything between 2 and 3 gets rounded down to 2. And then the same thing on the negatives. From a negative 0.9 to a 0, that gets rounded down to a negative 1. Okay, and like Sydney corrected me, anything from negative 4 to a negative 3.1 gets rounded down to a negative 4. What Desmos doesn't show you is that this graph has opened and closed circles. Okay, the closed circles correspond to saying that, yes, that is a part of the graph. And this would be a hole. Okay, believe it or not, the domain is all real numbers. Okay, it's because every integer in terms of x values is being taken into consideration. The range is all integers. Okay, and that'll change based upon the graph that you're working with. But the domain will always be all real numbers on a step function. Okay, and like I said, Desmos, they don't show the closed circles, whereas on your graphs, you want to have closed and open circles. Okay, so those are step functions. Like I said, we round down. And then the last type of function that you probably have had a little bit of experience with, maybe not a lot, it's called the absolute value function. Okay. And what the absolute value is it's taking the distance away from 0 on a number line. Okay, we're not necessarily dealing with positive or negative, but absolute value, 9 times out of 10, you're going to have a positive value because you're dealing with distances. So if we make a little chart, -3, -2, -1, 0, 0, 1, 2, 2 there, 3. Okay, so these would be kind of our x values that are plugged in. And we just want to talk about their absolute values. So the absolute value is talking about the distance away from 0. Okay, so if you have a -3, that's still 3 spots away from 0. It's just 3 to the negative side. So the absolute value of -3 is 3. The absolute value of -2 is 2. The absolute value of -1 is 1, because you're talking about distance away from 0 on a number line. So 0 is 0 units away from 0. 1 is 1 unit. 2 is 2 units. 3 is 3 units. And you can even plug in decimals, like 3.5 would still be 3.5 units away from 0 on the number line. So absolute value, since you're dealing in distances, you're dealing with positive values. Okay, you'll never have a negative at the very beginning once you take an absolute value. Okay, but that can change based upon the other items that are in the function. Okay, so let's get into it. So here, our first one, we're graphing a piecewise defined function, and we want to identify the domain and the range. Okay, so when you're dealing with these, you can see that f of x is x minus 1 if x is less than or equal to 3. Okay, and the process that you want to go through is you want to find what would this value be if I were to plug it in, because those are like stopping and ending points, because piecewise functions are discrete. They're not continuous. You have to pick up your pencil. So I'm going to ask myself, what would this function answer be if I were to plug in a 3 for x? So 3 minus 1 is 2. Okay, so I'd go to my graph. Got it here. And then I would plug in a closed dot. And once again, the closed dot is because it's greater than or less than or equal to. So it's encompassing -3 here. Okay, so that's my starting point. My next starting point is I want to know what would this function be if I were to plug 3 in. So it says f of x is equal to a -1 if x is greater than 3. So since it's a negative and it's a constant, or it's a -1 and it's going to be constant, what that's saying is that it doesn't matter what we plug in, anything greater than 3 is going to be a negative 1. So I'm going to go to 3. I'm going to put an open hole. Okay, because that one is just greater than, it's not greater than or equal to. So then once I have these points, I'm going to finish off drawing the pieces of my graph. Okay, and that's where your domain has to take into place. So starting with the bottom one, because it's an easier one, it says -1 if x is greater than 3. So that's telling me I need to go right all the way until positive infinity. There's no other breaking point there. So this graph is going to extend on forever, being -1 all the way to a positive infinity. Like that, just a nice horizontal line. And that takes care of the bottom function. Okay. Now working on the top one. It says that if x is less than or equal to 3, the equation is x minus 1. So I'm going to choose another point, and I'm going to pick an easy point to work with. So the one right next to it would be 2. So if I were to plug 2 in for x, I would get 1, because 2 minus 1 is 1. So I'd have my graph there. And then once again, you can see it's less than or equal to 3. There's no other stopping point there. So this top function is going to continue all the way until a negative infinity, whereas the bottom one continues all the way to a positive infinity. And then once I have my 2 dots, remember I have my stopping point here at 3, and draw my graph just like that. Okay, when you're talking about domain here, a lot of people will get confused because of the jump. The domain is still all real numbers. Even with the jump, and that's because I have an open circle on 3 here for my less or my greater than function, or the bottom function, and I have a closed circle. So since I have the closed circle, it's encompassed 3 into that domain. If this was an open circle and this was an open circle, then my domain would be all real numbers excluding 3, because I have an open circle here and an open circle here. But since I have greater than or equal to, or less than or equal to, on my top function, that causes the close. Okay, so they're not necessarily hard because you're just graphing multiple functions. It's hard because you got to pay attention to where the domain begins and ends. So step 1, we want to graph the linear function f of x, which is equal to x minus 1 for all the x that is less than or equal to 3. Since 3 satisfies this inequality, begin with a closed circle at 3, 2. That's what we did. Okay, and then they continue to graph it. I place the closed circle in the open circle because that's one of my most common mistakes. So I want to make sure I get that part right. Because if I can get that part right, I have a high chance of getting the problem correct, as long as I pay attention to my domains. But there's multiple ways to skin a cat. They chose to graph the top function first. Okay, step 2, graph the constant function, which is f of x is equal to -1 for all x values that are greater than 3. Since x does not satisfy the inequality, begin with an open circle at 3, -1, and draw a horizontal ray to the right. So that's that bottom equation right there. So if you can break it up into multiple pieces and pay attention to where you have a closed dot and an open dot, it's a pretty easy section when you're talking about piecewise function. Okay. The values are the y coordinates of the points. The domain is all real numbers. The range here is cut off because our highest point is at 2. So y must be less than or equal to 2. Okay. So here we got another one. It says graph f of x, which is equal to 2x plus 1 if x is less than or equal to -1. And then -3 if x is less than or equal to -1. Identify the domain. So I'll copy it down, f of x. (2x plus 1) -3. Okay, and then we just repeat the same process. So the first thing that I'm going to do, like I said, is I want to plug in -1 into this top equation. Okay, this one's going to have an open circle because it's just greater than. So if I plug in a -1 times 2 is a -2, plus 1 is a -1 with an open circle, just like that. Okay, if I want to finish off this graph, since it's x is greater than -1, the next easiest point to plug in would be 0, because 0 falls within this domain, and it makes my life pretty simple. When I plug in 0, 2 times 0 is 0 plus 1. I get the point 0, 1, and then I have enough information to finish that portion of my graph. Okay, and that's the top function. For my bottom function, says that as long as x is less than or equal to -1, my y value is a -3. So since it has less than or equal to, I put my closed dot. It's a constant function, so I can draw it this way. So my domain, once again, because I have a closed dot over a closed dot under an open dot, my domain is going to be all real numbers. And then my range. Okay, so here the range is the tough part, because we know that it's -3. So -3 is an applicable answer here. I don't know who's talking, but so it has to encompass -3 for the bottom here, and then its y is greater than -1. Okay, and there's multiple different ways to express the range. Just you want to have that information listed to answer the question, since the question asked for it. So here they have the graph. Once again, open circle at -1, -1, the ray going up there, closed circle at -1, -3 with our horizontal constant. And then we have multiple choice to determine the range and domain. So A can't be it because it has the range being all real numbers, and this graph doesn't extend to a negative infinity, so that can't be it. The domain, all real numbers, range, y must be greater than -1. Well, that's true, but that doesn't encompass this -3 here. So C, domain, all real numbers, range, y is greater than -1 or y is equal to -3. That seems correct. Domain here, they have that cut off. That's incorrect, so the correct answer is C. Okay. So here, we're being asked to write a piecewise function. Okay, so this one, it has a constant, and it has 2, and then it has a ray. We want to pay attention, make sure you can identify any critical points if possible. Like if they give you a y-intercept like this graph does, that makes your life a whole lot easier. We're going to have to find the slope of this line. This one's a constant, so we don't have a slope to really worry about. But we really want to pay attention to where our closed dot and our open dot is. So we have a closed dot, and it looks from the graph that f of x is equal to 1 when x is greater than or equal to 2. Okay, and that's coming from this top point here. Okay, the greater than or equal to gives me, because I have a closed dot. Closed dot here, and the graph stays at 1. It's my constant. That x value is 2. So that's my border. So to express that, I would write f of x is equal to 1 when x is greater than or equal to 2. It identifies the closed dot, it lists out what the value is, and it gives me my starting point, and it gives me what the f of x value is. It's pretty easy to write a constant function. But when you're looking at the other one, this bottom portion of the graph, here's where we really want to pay attention. Okay, so this point, 1, 2, 3, 4, beneath the origin, it's -4. So that's our y-intercept. We can apply what we know about slope-intercept form. We have the y-intercept. So we know our equation has to be something -4. We're going to have -4 as the constant because it's your y-intercept. So now we want to think about slope. Here we can start from the graph, and we can pay attention to grid lines, or we can pick 2 points and actually run the slope formula. So first, just to graph it, and then I'll confirm it using the slope formula. If I go to the left, I have to drop 1, and then I go left 1. Okay, and then you see how I cross on a grid line. It's an easy way to find the slope. Okay, remember, slope is always expressed in rise over 1, rise over run, or the change in y over the change in x. So as we went to the left, y had to go down 1, and then x went left 1. So that's -1 over -1, which simplifies down to 1. Okay, and I can find that slope from the graph. Okay, this is change in y. This is change in x. Okay, and you can pick that up by using the graph. That's totally cool. It's not the best way to do it because anytime you're doing that, it's an approximation. Okay, this one was handy because it fell upon grid lines, but not every situation is going to be like that. So we can use the slope formula, which is m is equal to y2 minus y1 over x2 minus x1. Okay, and then we just have to select some certain points. So I'm going to go back to the graph. I'm going to choose the point. Looks like 2, -2. And then I'm going to choose the next point as 0, -4. Okay, so these are the points that I identified. Once again, I already have my y-intercept, so the graph was nice for me to have that. If I don't have that, then I just run it through the slope point slope formula. Then I take these, I'm going to plug them into there. Okay, so I'm going to have -4 minus a -2 over 0 minus 2. Voila, just like that. So -4 is going to give me -2. 0 minus -2 is -2. -2 divided by -2 simplifies down to be 1. So my slope equals 1. Okay, like I said, I already have my y-intercept. So this is pretty easy, is x minus 4 when x is less than 2. Okay, once again, I have an open circle, so it has to be less than. I identify the domain that it has, and then this is the function that we plug in. Okay, this was an easy one because they gave me the y-intercept. In the event that you don't, or you're not given the y-intercept, what we can do is we can run it through the point slope formula. I'll show you how to do that one more time. I know it's something that we've already covered, but it never hurts going back through. So remember, m is your slope. Y1 is just a generic point that's plugged in. Okay. X1 is the other point that we plug in. So if I use -2, 2, -2. So I'd plug in y minus a -2 is equal to 1. So my slope was 1 times x minus 2. Okay, then I'd simplify. So y minus a -2 turns into y plus 2. I distribute. 1 times x is x. 1 times a -2 is a -2. And then I just isolate my y variable by subtracting 2 from both sides. I'd have y is equal to x minus 4, or f of x is equal to x minus 4. Then all that would be left is to put my domain in, just like that. Nope. So after you get it to this point where you simplify, we just isolate the y variable, and then that is in slope-intercept form. But like I said, this one was pretty simple because they gave us the y-intercept, and we could count the slope from the graph. It's not always going to be that simple. Okay, you have point slope that works the same way. All of you know how to find the slope just given 2 points. So that's all going to come into play. Okay. Okay, so identify the piecewise defined function shown in the graph. Okay, we have multiple choice question here. The easiest thing to do is to start to use the closed dots and open dots to be able to help filter out some answers. So looking at the top one, so 7 if x is greater than or equal to 4. Okay, so here they have a -4 and a 4 on answer choice A. Looks like both endpoints are at -4, so that one can't be it. Answer choice B, once again, they've mixed up endpoints, so they don't stop at -4 and 4, so that can't be it either. Answer C, 7 if x is less than or equal to -4. Okay, 2x plus 10 if x is greater than 4. Once again, they've messed up endpoints here. The only one that has the correct endpoints are -4 and -4. But to double check ourselves, 7 if x is greater than -4 has a closed dot. That checks out. Okay, if I plug in the point -5 here, -5 times 2 is -10 plus 10 is 0. That would be that point right there. Okay, I could settle with D. It's the only one that has the correct borders or endpoints. And when I plugged in points, they both worked. This is one where we would have to run it through the point slope formula. Okay, because we're not given the y-intercept. We could try our best to extend that line, but graphing is just an estimation, so that doesn't really, it's not the best way to get the answer. Okay, so using a step function. It says one psychologist charges for counseling sessions at the rate of $85 per hour or any fraction thereof. Draw a graph that represents this situation. Okay, so here we gotta pick out important information. So he's $85 an hour or any fraction of an hour. So what that means is if we go in for half an hour, we're paying $85. Okay, if we go in for 1 hour, paying $85. Okay, if we go in for one and 1/3 hour, so an hour 20 minutes, Okay, here we're paying 170. Okay, because this is 1 full hour at 85 and then a portion of another hour at 85. Okay, so what if I go in for 2.5 hours? Okay, well, I have to pay 2 full hours at 85 bucks a pop, which is 170, and then half of another hour, which makes my price 255. And building this table kind of helps. Okay, makes it pretty easy in that sense. Okay, and what our graph would look like, I'm going to draw a step function here, and we're not going to go into the negative because we can't have negative hours. So I have 1 hour, 2 hour, 3 hour. 1, 2, 3. So anywhere between 0 and 1, I'm paying, mark 85, 170, 255. So anywhere between 0 and 1, I'm paying $85. So that means I have a closed dot on 0 and an open dot on 1. Okay, and then anything from 1.1 to 2, I'm paying $170. And anything from 2.1 to 3, paying $255. Oh, I made a mistake. Dang it. I hate it when I do that. Okay, the mistake I made is I drew my closed dots on the wrong side. And it took me a second to conceptualize it, that if I have 0 hours, I can't really have 0 hours of time spent. So it would make more sense to have my open dot here. So I'll redraw it because I messed it up. 85, 170, 255, 1, 2, 3. Okay, so I'm going to have an open dot and then a closed dot. Open dot and then a closed dot. Have an open dot and then a closed dot. Okay, and it takes a little bit of practice to get familiar with the open dots or the closed dots. You just want to ask yourself, does the information in the graph, is it logical, right? Does it make sense? Is it conceptual? So here I'm dealing with time. Okay, so I don't know about you, but I've never made an appointment and been charged $85 for a 0 hour appointment. Okay, I've paid $85 for 15 minutes, but never for 0 hours. So that's what I had done wrong on the first one. So I need to have the open dot on 0, and then anything under 1 is $85, or anything up to 1 is $85. But the second I get above 1, the minute I get above 1, I'm like an hour and 1 minute, I'm paying 170. Okay, and then that stays until I hit 2 hours. And then 1 minute over 2 hours, I pay $255. So your graph, you really want to think about it, especially with these step functions, because they're easy to make mistakes on, having the open dots and the closed dots. But you just got to ask yourself, is it logical? Does it make sense? Especially in a real world aspect, we can't have 0 hours. They're not going to charge you $85 just for setting up the appointment. You actually have to go to it. Okay, so the total charge must be a multiple of 85 for the graph. So the graph will be a function. So the graph will be a graph of a step function. So if the session is greater than 0 hours but less than or equal to 1 hour, the cost is $85. The time is greater than 1 but less than 2 hours, it's 170, and so on. So we used the pattern and they built a table. Same way that we did, the table can have any format. They just conceptualize it, and this makes it a little bit easier. You can see that they're going to have the open dot on 0, the closed dot on 1. Open dot on 1, closed dot on 2, open dot on 2, closed dot on 3, and so on. Then they take this information, and then they plug it into the graph. So an open dot at 0.85, close all the way until 1, then we jump up to 170, jump up to 255, 340, 425, 510, 595 for the cost of your therapy sessions. And the key is fraction thereof. Okay, fraction thereof says that you may not get a full hour, but you're going to be paying for a full hour. Okay, another way that you can look at it to help identify the open and close is right there in that check. It says, since the psychologist rounds any fraction of an hour up to the next whole number, each segment on the graph has a circle at the left endpoint and a dot on the right endpoint. So a helpful note that you could write is if we're rounding up, open left end, closed right. And if we're rounding down, it's going to have a closed left and an open right end. Once again, that's talking about the open and the closed circles here. Okay, so the daily grind charges $125 per pound of meat or any fraction thereof. Draw a graph that represents this situation. So here we want to be thinking about, are we going to be rounding up or rounding down? Okay, so meats per pound is the x-axis. It's any fraction thereof. So we're going to be rounding up. So we can eliminate a couple of these graphs. We can eliminate graph A because that's more of a 0. No, we can eliminate graph B because that's more of a rounding down situation. We can eliminate graph C because that's a linear one and it takes into account the price of 1.5 pounds. Since it's per pound or any fraction thereof, we're dealing with whole numbers. Okay. D, it's cut off and it doesn't list out anything for 3. So answer A looks like it's going to be the most prominent one. So from 0 to 1 pounds, I'm paying $1.25. That makes sense. From anywhere above 1 pound to 2 pounds, I'm paying $2.50. Okay. Anywhere above 2 to 3 pounds, I'm paying $1.75. That one checks out. So answer A is going to be the correct answer. Once again, we're rounding up. So we have open left and a closed right end. If we're rounding down, it would be answer B. But since we're rounding up, okay, I'm going to give you guys a couple minutes to write some stuff about absolute value functions. I got somebody who's pulling up in my house. Okay, that was weird. All right. So hopefully you've gotten a little bit down about parent functions of absolute values. Like I said, absolute values, you're dealing with distance away from 0. Okay, so since you're dealing with a distance, it always corresponds to a positive number. That's what causes the V shape. Okay, absolute value functions, the way that they're presented to you is they are listed as f of x or whatever variable they choose. It'll have one bar, the variable like that. Okay, what we have to understand is in order of operations, these are treated as parentheses. Okay, so we take care of whatever happens inside first. Okay, A couple other things that'll help you with this is translations and transformations. Okay, as a general rule, these will apply both to your step function and the absolute value functions. Okay, so if I were to write it like this, it's just a generic a absolute value of x minus h plus k. Then I'll write a step function in the same way as a double bracket x minus h double bracket plus k. Okay, so these are the two general forms. This is absolute value. This is your step function or the greatest integer function. Okay, A is what's known as the vertical dilation factor. Okay, this stretches or compresses the graph. Okay, in other words, it makes it tall and skinny, kind of short and a little wide in terms of the V. So if A, the absolute value of A is greater than 1, it stretches it. The absolute value of A is between 0 and 1, that compresses. Okay, so if A is 1 or greater, that stretches the graph. If it's between 0 and 1, and we're talking about absolute value, okay, it's going to compress the graph. So this would be long and skinny. This would be kind of short and a wider triangle. Okay, if you have a negative A value, that flips it over the x-axis. Okay, and the beautiful thing is these rules still apply to your step function. So if this is 5, then it increases the graph. Let me pull up Desmos so I can actually show you that. 4 of x. Okay, so here in red, I have just the floor of x. Okay, here in blue, I have 5 times the floor of x. So I've plugged in 5 as my value of A, and you can see that it stretched my graph vertically. Okay, if I were to plug in 0.5, 4 of x, that's going to be in green. And here's my first red. You can see I've had 2 greens before I get it. So that's compressed it. So the decimals in the A value compresses it. A positive value other than 1 is going to stretch the graph. Okay, that's also the same thing for absolute value. Just need my calculator. So if I go absolute value of x, there's the original one. I go 0.5, absolute value of x. There's the compressed one. If I go 5 times the absolute value of x. Okay, so this purple one here is the original. That's just the absolute value of x. This black one is with a 0.5 for the value of A. You can see it's compressed it. And then this red one has a vertical stretch. Okay, that way you're not caught off guard. Okay, H and K. These two. H, since it's on the inside, is horizontal slide. Okay. K, since it's on the outside, is a vertical slide. Okay, and it's always set out to be a minus. okay, for H in terms of the horizontal slide. So if it's anything on the inside, x minus 5, x minus 3, that's sliding to the right. Okay, if it's x plus 3 or x plus 5, then that's sliding to the left. But a negative corresponds to a right slide. Negative corresponds to a slide to the right. Your vertical slides, if it's a plus, it's sliding up. Okay, it's moving the graph up. If it's a negative on the outside, it's sliding the graph down. So let me get back to Desmos. And these are true for both absolute value and the step function. So I'm just showing you examples. So if we take the absolute value of x minus 3, you can see it's the same graph, it's just been slid to the right, or slid to the right. Okay, if we take the absolute value of x plus 3, it's going to be the same graph in green here, but this one slid to the left, whereas the minus on the inside slides it to the right, and the purple one is your original. Okay, so now if I have no horizontal translation and just a vertical translation, you can see that my blue one, which is the absolute value of x plus 3, has slid the graph up, and the absolute value of x minus 3 has slid the graph down here in green. So outside is your vertical transformations, inside is your horizontal transformations. Okay, that's not the biggest part of the entire section. It just helps when it comes to some of the problems. But like I said, you have the availability of Desmos. You can plug in almost anything. But the quicker you can get with those in your head, the better off you'll be. Just like with anything, practice makes perfect. Okay, so here we go. I'll talk about parent function domain. Okay, so going back to just the parent function, what we have to realize is paying attention to the domain and range. Okay, your domain for an absolute value function is always going to be all real numbers, and that is the same for a step function, always all real numbers. However, the range is going to change. Okay, with an absolute value function, if it's pointed like this, you're going to have a minimum value of the range. So in this case, y is not going to be less than 0. Okay, if it was the absolute value of x minus 2, y is not going to be less than negative 2. Okay, but your domain is always all real numbers. If it's a negative absolute value, where it's a v pointed down, so it has a negative 1 for the a value, in other words, that's going to have a maximum. Okay, or in other words, there's going to be a range value that's cut off that you cannot exceed. Okay, so here, graph y equals the absolute value of x plus 1. This is just a vertical transformation. So since it's on the outside, that means it's going to be the absolute value of x shifted 1 up. But we can do this by just creating a table. To emphasize my point, I'm going to choose negative 2, negative 1, 0, 1, and 2 for my x values. I'm going to have y values. So we already know it's shifted 1 up. So if I plug in 0, the absolute value of 0 is 0 plus 1 is 1. Remember, these act as parentheses. So we have to take the addition multiplication on the inside and then take the absolute value of it. And then we handle everything outside. So when I plug in negative 1, the absolute value of negative 1, or the distance away from 0, is 1 plus 1 is 2. Okay, negative 2, absolute value is 2 plus 1 is 3. 1, the absolute value of 1 is 1 plus 1 is 2. The absolute value of 2 plus 1 is 3. Okay, and what you'll find is that this graph has line symmetry. Okay, or in other words, wherever this point is, my y values are mirrored. So in this case, 0, 1. So I have this point, this point, this point. Is I can divide this graph into a left and right side and then fold it upon itself. It helps knowing that, because if I plug in one value of points, I already know what the other side should be because it has line symmetry. But the domain, all real numbers. The range, this one has a minimum value of 1. So y must be greater than or equal to 1. Just like so. So we created a table of values. Okay, they expanded their table. Once again, you can see there's a minimum point. Connect it, and that's what your answer would be. The domain is all real numbers. The range is y is greater than or equal to 1. Okay, so here's where knowing what your inside and outside are. Okay, so remember on the parent function, it always starts at 0, 0. Okay, the point is always on 0, 0. Looking at this point, it's been shifted 1 to the right. So I'm looking for one that has a -1 on the inside, but then it's also been shifted 1 down. So I need a -1 on the inside. I need a -1 on the outside, which corresponds to answer B.